Hello everyone, it's time for more organic chemistry, and now we're going to discuss alkyne reactions, the carbon-carbon triple bond functional group doing some reactions. We're in Key Concepts, Unit 3, Part 1, having all kinds of fun. Yep. Let's look at some similarities between double bonds and triple bonds, and that's actually the saving grace here. So definitely go back and review your alkene, carbon-carbon double bond reactions, because knowing those will help you remember the triple bond reactions. It's not a universal pattern, but it happens quite enough. So if you know this pattern, meaning that you know what a double bond does, usually there's some reagents that will remove the pi bond, change a double bond into a single bond, and then add some reagents, add some atoms or functional groups. That's the usual reaction pattern for alkenes. Alkenes have one pi bond and then adds one set of reagents. Well, the triple bond has two pi bonds, so just do the alkene reaction twice. Each pi bond gets to add some reagents, and you can just, there's two pi bonds, it happens twice. Okay, so let's take a look at three alkene reactions we saw before. HCl, Cl2, and hydrogen and palladium. So we'll just kind of put here review. Let's start with propene and add hydrochloric acid. And then we have to remember, okay, how does this work? Markovnikov addition, meaning that the rich gets richer. The hydrogen HCl goes to the carbon with more hydrogens. And then the leftover piece goes to the other carbon. This mechanism also occurs through carbocation rearrangements. Oh, sorry, carbocation intermediates, so we have to watch for rearrangements. None here though. The secondary carbocation can't rearrange to go tertiary, so there's only one product. That's nice. I'll take the same molecule and treat it with chlorine gas, Cl2. And it's an addition reaction. The double bond becomes a single bond, and two atoms of chlorine go across which used to be the double bond. You actually get anti-addition. So if the double bond was on a ring, the chlorines would be trans. Last reaction is hydrogenation. So take hydrogen and your favorite catalyst, palladium or palladium on carbon, platinum, even nickel will work. Not very well, but it's cheap. And you get an alkane. Cool. Okay, so knowing those can help us do the triple bond reaction. And again, here's the pattern up here, and I'll lose that in a second as I scroll down. Alkene, one addition reaction. Alkyne, you get the reaction to happen twice. And oftentimes you can do it sequentially, meaning you can have the reaction go once, wait, and then do it a second time, or maybe you don't even have to. Little point about the triple bond, right? So if I draw out, what is this, a condensed formula? What's the hybridization of the carbons involved in the alkyne functional group? Well, they're sp hybridized, the bond angle is 180. So they're supposed to be linear or straight. However, I still zigzag my chain even though they have alkynes, even though the carbon's supposed to be linear. And the reason I do that is because if someone draws an alkyne in the right shape, now I'm a little confused. How many carbons are in this chain? Are there 3 or 2? Did someone just get sloppy and this is 2 carbons? Or is there really a middle carbon there? So I zigzag just to make it clear. So be aware that's how I draw my skeletal drawings. And a lot of people do that to clarify the number of carbons in the chain. But we'll have to remember, wait, that's sp, it's supposed to be straight in case someone asks for a bond angle. All right, so let's repeat the same reactions. Let's add HCl. And what we can do is remember the pattern. The triple bond can react twice. So if you want, just add enough HCl so it can only react one time. You can either write the word 1 mole in front of HCl, meaning, hey, if you started with 1 mole of the triple bond, just add the same amount, an equivalent amount, 1 mole of HCl to get it reacting 1 time. But what if you have half a mole? Well, then you need a half a mole of HCl. What if you have 10 moles of the alkyne? Well, then you need 10 moles of HCl. Okay, so instead of saying 1 mole and being really specific, most chemists will then say 1 EQ, 1 equivalent. Maybe you saw that unit back in general chemistry. If you haven't, equivalent just means use the equivalent number of molecules or the equivalent number of moles, so it happens 1 time. Cool. So it doesn't matter how many moles of the alkyne you have, use an equivalent, 1 equivalent of HCl, and that guarantees the reaction can only happen once. So the pattern here is only 1 pi bond disappears, just like up here. The 1 and only 1 pi bond disappeared to form a single bond. So now, if I add 1 equivalent, I lose 1 pi bond, but I get to keep the other one. So I'll choose to lose this outer one. Doesn't really matter. You could choose either pi bond to leave. And the reaction occurs by Markovnikov addition. The rich gets richer. It still happens here too. That's nice. So the end of the triple bond has a hydrogen. This triple bond carbon does not have any. So this carbon at the end is rich in hydrogen. So hydrogen goes here, meaning the other carbon gets the chlorine. So that's Markovnikov addition, just like it was before. Look at the structures are very similar. This one had 1 pi bond, goes a single bond. This had 2 pi bonds, now it has 1 pi bond, similar structure. And then you can add another equivalent of HCl, or you can just write HCl. I want you to be aware of the notation here. If you specify 1 EQ, then you're trying to be exact. If you don't use EQ or mole, it typically means you're adding an excess of HCl. Back in general chemistry, we would say the other compound becomes the limiting reagent. And we use an excess of the cheaper agent just to make sure our most expensive molecule, the limiting reagent, gets all used up. Yeah, the organic compound in organic chemistry is the most important molecule. So let's add enough reagent so that all the organic molecule gets a chance to react. So the assumption is you always use an excess. So even up here, the top of the screen, I didn't write 1 EQ or anything. We're using an excess of HCl. This reaction uses an excess of chlorine gas. This uses an excess of hydrogen gas. Palladium is a catalyst. So you really don't need an excess. It's a catalyst. It doesn't get used up. There you go. Enough about that. Add some more HCl, and now it follows this pattern. It is an alkene. It's a carbon-carbon double bond. So, hey, rich gets richer. There's 2 H's on this carbon, none on this one. So the hydrogen goes to the end, and chlorine goes to the middle carbon, and you lose the pi bond. So now, if you have 1 pi bond, you get 1 chlorine. If you have 2 pi bonds, you get 2 chlorines. I like that. Nice symmetrical pattern. Okay, let's try Cl2. And again, you can say, well, maybe you only want to do the reaction 1 time. So I'll add 1 equivalent of Cl2. So, whoops, we're trying to do the triple bond reaction. If you had a single bond, 1 pi bond, a double bond, you get 2 chlorines. That's what happened with Cl2. If you had 1 equivalent, then you keep 1 pi bond and you still add 2 chlorines. How come they're on the same side of the double bond? Because they're not supposed to be. It's anti-addition, which means we're supposed to be on opposite sides. I'm glad I caught that. Whoops. I'm supposed to erase this chlorine before I did that. Gotta fix that. I'll abbreviate addition this way, anti-addition, which means the chlorines add trans, right? This is an alkene, it's kind of locked in position. It's trans, and now we can add a second equivalent, or just an excess of chlorine, and now the pi bond, that's an alkene, this is an alkene. The new chlorines add anti, it doesn't matter, because now you have a straight chain, and there's two chlorines on the carbons that used to be triple bonded together. Oh, by the way, if you're writing an exam answer and, or, you know, for whatever reason, maybe a homework problem, whatever, and you don't want the alkene intermediate, or that's a product, you don't want to stop here and you want to go from the triple bond all the way to the molecule with 4 chlorines, you can just do it in one step. You can say, hey, take that triple bonded molecule, add Cl2, and remember, we're going to assume we're using an excess. So if you just see Cl2 all by itself, it means as much as you need to get the job done. Every pi bond gets chlorine. And so you get 4 chlorine atoms all together. And notice I didn't pay particular attention about spraying this cis or trans because single bonds are free to rotate. And you can spin this to put the chlorines wherever you want. All right, last reaction, hydrogenation. That happens by syn addition. Just as a quick reminder, if we had cyclohexene, or let's do dimethyl, 1,2, dimethyl cyclohexene, true with hydrogen gas, maybe I'll put platinum this time, doesn't matter. What happens is the hydrogens add syn, by syn addition, same side, cis, and now the methyl groups have to lie on wedge bonds. And if I stick to just a pure skeletal drawing, that's good enough. The end of the wedge bond, no elements given, so it's assumed to be carbon. Those are methyls. Syn addition is the key. Okay, so let's take the triple bond and hydrogenate it now. So let's take the triple bond, add 1 equivalent of hydrogen gas over a palladium catalyst. What do you get? Nature. And exceptions to the pattern. Nature, she makes all the rules. You go in the lab, you carefully measure things out, 1-to-1 ratio. You're expecting an alkene. You go into the lab, you discover you got an alkane, and you have leftover triple bond. You cannot, that's what the next line is going to say. Back up. The limitation of this reaction, hydrogenation with palladium or platinum, whatever, with alkynes, you can't make alkenes with it. Why not? Well, I didn't ask you to memorize the mechanism for hydrogenation, but we did go over it. Remember, there's a metallic, it's the platinum or palladium surface, and in the mechanism, the hydrogen gas sticks to the surface, splits apart into individual hydrogen atoms, and gets tied up on the surface of the catalyst. And then the alkene, the pi bond, will sit down the surface and the hydrogen will add to it. It's the same mechanism with the triple bond. The hydrogen's always all over the surface of the catalyst. The triple bond sits down, 2 hydrogen atoms attack it, and before it has a chance to lift off, the other pi bond gets immediately attacked, which means you can't stop it. Once the catalyst reacts with 1 pi bond, it immediately reacts with the second one, and you take the triple bond directly to the alkane. And if you said, well, I only use 1 equivalent, sorry, the way nature does is first come, first serve. The first alkyne to hit the surface gets all the available hydrogen. And there'll be some triple bonds that never collide with the catalyst, and the ones that do get all of them, they go right to being saturated. Turns into an alkane. So don't add 1 equivalent because then you have leftover triple bond. So basically this reaction is add hydrogen gas because you can't stop it. So add enough or add an excess to make sure that all your triple bond reacts. It'll be, the triple bond will be the limiting reagent. Okay, so it's good to know. But it's not good to live with. Chemists are like, dang it, I want my double bonds out of my triple bonds. And so this guy named, I had to go look it up. His name was Herbert Lindlar. Herbert Lindlar was like obsessed with this idea. It's like, there's gotta be a way. And he thought about it for a while, and he knew the mechanism. At least this is how I understand it. Paraphrasing the story a bit. He realized that catalyst is just too robust. It's too good. We need to weaken that. We need to slow down the catalyst so that after the first pi bond reacts, the catalyst needs to be weakened so that the alkyne, or what used to be the alkyne, could leave before the second pi bond gets attacked. And he knew a little bit about poisons. So lead is a poison. Try to keep that out of our food, right? Don't eat lead-based paint, mercury, things like that. It turns out a lot of those poisons actually slow down or disable nature's catalysts, enzymes. And that's how a lot of poisons act in our bodies, because they inhibit the enzymes that keep us alive. Anyways, he knew a little bit about that and thought, what if I try and treat my palladium catalyst with a little poison, a little lead, maybe mercury. Turns out lead did the trick. Not ideally, but he added some lead acetate, I believe it was. Look at my notes real quick. Yeah, lead acetate. And another organic molecule called quinoline, and a little carbon, a little calcium carbonate. Anyways, a little trial and error. He found a way to weaken the palladium catalyst, and so it started to work. So you don't have to know the recipe. All you have to know is Lindlar's catalyst. So if you use the weakened form of palladium, and the ingredients are listed in the text here, you don't have to memorize it. There it is. It's lead acetate, calcium carbonate, quinoline. All you have to do is say, okay, I want the double bond, so I'm going to use Lindlar's catalyst. And if you just write Lindlar instead of PT or PD, that's a signal, hey, you're using the weakened catalyst. You do stop the double bond, and you don't have to add one equivalent. You can add an excess of hydrogen. The catalyst is that good. It just knows convert the triple bond to a double and stop. Pretty cool. There's something else about that. Oh, yes. It's still a heterogeneous catalyst, meaning that the catalyst doesn't dissolve in the solvent. The mechanism is still the same. Triple bond comes down and rests on the surface, and the two hydrogens attack from the same side. It's still syn addition. Just like it was up here. Hydrogen gas on platinum surface, whatever, syn addition. So same thing with Lindlar's catalyst. So if you have a triple bond that's not at the end of a chain, but the triple bond's in the middle or something, and you say, okay, I want to take that double bond and take that triple bond, make it a double bond with Lindlar's, then you're going to make the cis product because the two hydrogens add to the same side because of syn addition. You don't get the trans. Let's see if there are other notes about hydrogenation with Lindlar's catalyst. I think I mentioned all that takes place in the catalyst. You have to remember syn addition. Hydrogens always add cis. You always get cis products from your triple bonds in Lindlar's catalyst. So it says right here. I'm not going to ask for the mechanism on the test. Okay, cool. Or not so cool. There's some scientists out there like saying, dang it, what if I want a transalkene? Lindlar, help me out. Well, Lindlar probably worked on the problem, but I don't think he solved it. So what currently works is the dissolving metal reaction. It's kind of cool. What you do is you take your triple bond, and let's take the triple bond that's in the middle of 4 carbons. And don't use hydrogen gas, oddly enough. Hydrogen gas with all those metal catalysts kept giving syn addition. This is the reaction where we want trans, so you want the anti-addition product. And it turns out you either use lithium metal or sodium metal. Don't put a plus here. Na plus is not the metallic form, that's an ion. So you actually just use elemental sodium or lithium, they both work. And then you have to cool ammonia. Pure ammonia is a gas at room temperature. but use some dry ice to cool it down so it liquefies, and that's your solvent. And it turns out when you put metallic sodium or lithium into ammonia, the little chunk of metal that is sodium starts to dissolve. That's kind of cool. It dissolves in ammonia. And what actually happens, you know how sodium and lithium are alkali metals, they like to donate one electron. They kind of do that to the solvent. And in a sense, the electrons are kind of dissolved in there too. It's not exactly accurate, but it's a very reactive solution with many available electrons. And it turns out it's a great reducing reagent. And that's what happens. The triple bond's reduced to a double bond, and you always get trans. It's through anti-addition. Okay, whoops. I'll abbreviate addition that way. Yeah, trans only, occurs by anti-addition. This one, everything does dissolve, hence the name, dissolving metal reaction. I am not requiring the mechanism on my exams, but it's still a cool one. So I will post the mechanism on Canvas just in case you're curious, but it's not going to be on the exam. Nice. Okay, so now we have ways of taking the triple bond and going directly to an alkane. You just use hydrogen and your favorite metal catalyst, nickel, palladium, or platinum, or platinum oxide, palladium on carbon. You can use all those here. Or you can make the cis alkene with Lindlar's catalyst and hydrogen gas. Or you can use sodium with ammonia to get the trans alkene. Lots of choices, lots of power, whatever you want. Cool. Okay, that takes care of this column of information. Awesome. Are you having fun yet? I like puns. I like memes. I like distractions. Okay, stop it. You're back on track. Okay, again, we're trying to get through the triple bond set of reactions. It's really helpful to remember your double bond reactions. So we had one with mercury, right? We'll go back to propene here. And this one had a lot of reagents. You take mercury acetate, THF, and water, mix it with your alkene, let the reaction go a while. That's what the 1 stands for. First reaction, 3 reagents with your substrate or your alkene, let it react. When it's done, add another reagent to do a second reaction, reaction number 2. And the net outcome is Markovnikov addition with no carbocations. That was the choice. I mean, otherwise, if you didn't care about carbocations, you just use hydronium ion. And it also does Markovnikov addition. But you get carbocations, which can rearrange. Markovnikov addition means the rich gets richer. This alkene carbon has 2 H's. This one only has 1. And this one gets more rich in hydrogens. So hydrogen goes here, and an alcohol goes here. And the scientists say, yeah, that's nice. I want the alcohol, but I don't want the rearrangement. So use this set of reagents to avoid any carbocations and any chance of rearrangements. But you get the same product. So, hey, what's the triple bond going to do? Well, it's the same pattern. The pattern is lose the pi bond, add an alcohol. So if you treat the triple bond with these 4 reagents, you do get the same product initially, following the same pattern. You take away 1 pi bond, so 1 is still remaining, and you add an alcohol. But then people discovered that the triple bond seems to be a little bit more reactive than the double bond. And in fact, you don't have to wait and do like step 2 later. The reaction's like over with just the mercury and water. And in fact, it works pretty well. Don't need the 1 and 2. If you just use mercury sulfate, a little sulfuric acid, and water. Okay, so see the pattern here? We have HgSO4 and H2SO4. So it's almost like writing H2SO4 twice, but change the G to a 2. And then you got water in there too. So what's really happening is you have mercury, you have water, but instead of the THF co-solvent and later sodium borohydride, a little bit of acid is enough to get the reaction to go. Let's get to the nitty gritty, the bottom line. Which set of reagents to put on the exam? I'll accept either one. When I'm writing the reaction though, I'm going to use the easier one, the mercury sulfate, sulfuric acid, and water. Those will be my choice of reagents. If you use the top set of reagents on your triple bond, you get the same product. Turns out this is an intermediate. Nature, she makes the rules. So the product, yeah, they match. It's following the pattern. Lose one pi bond, add an alcohol. That's what happens with the double bond. If you have a triple bond, you still lose one pi bond, add an alcohol. And nature kind of looks at that and says, something just ain't right. I don't like this. This carbon right here is both an alkene and it also is attached to an alcohol. I want that oxygen to have the double bond. This is actually the name of a new functional group. So if you have a carbon that's both an alkene carbon and an alcohol carbon, you can call that the Enol functional group. The don't you love this? Alkene plus an alcohol. So take the En and the Ol and make a new word out of it. Scientists love this. Oh my goodness. So the Enol functional group turns out to be not very stable. Nature, she makes the rules. In fact, there are some enols that are stable. We'll see them next semester. But here in the first semester, if you're reacting with the triple bond, all of the enols that you'll see in this section of organic chemistry will be unstable, and that's not your final product. You have to rearrange this. So you need this pi bond to go to the oxygen. So I'll put a little arrow here, and you get a double bond to the oxygen. And then this other carbon, well, yeah, it's still there. This is a ketone then. Some of you might be asking, where'd the H go? It's hiding in our skeletal drawing, right? So how many hydrogens are on this carbon right now? Well, this carbon's making a double bond, so I see 2 of the 4 bonds. It's missing 2 bonds. It must be 2 hydrogens here. Here's that same carbon afterwards. How many hydrogens are on that carbon now? 3. Yeah, so this hydrogen, I don't want to use a curved arrow because curved arrows show movement of electrons, but this hydrogen moved to this carbon and the pi bond moved up here to the oxygen. It was a rearrangement. Scientists love adding new words to every new idea. Hey, this rearrangement caused an enol to become a ketone. But you know what? There's 4 letters in enol, so I'm only going to take the first 4 letters of ketone and call this a keto enol rearrangement. Now, let's spice it up with more sciencey term. It's a keto eno tautomerization. Yeah, totally made up word, but great search term if you want to learn more about it. Yeah, really, that's actually the name of this rearrangement, a keto eno tautomerization. Not on my tests, but we're going to see that term pop up a couple times throughout this whole year of organic chemistry. And now we know what it's referring to. The enol group changing into a ketone group, keto eno tautomerization. Bottom line, take an alkene with mercury, you get an alcohol. But take an alkyne with mercury, you get a ketone. So the pattern might be thought of, always add an O in a Markovnikov fashion, but if you have 1 pi bond, you just have 1 single bond. But if you have 2 pi bonds, you actually keep a pi bond, and the O is not single bonded O, it's double bonded O. It's a ketone. That's the pattern. That's what we'll have to remember. What else do we have to remember? Let's just review the notes here. Yep, we said Markovnikov's rule is followed. The carbon with more hydrogens gets the hydrogens. The other carbon has fewer hydrogens. Yeah, that one got the oxygen through a double bond. And yay, no rearrangements. The last two steps of the mechanism, which we're going to see in a second, is the keto-enol tautomerization. There's where it comes from. Tautomerization is catalyzed by acid. So next semester, we're going to see two ways to do the mechanism of keto-enol tautomerization. One is going to be assisted by acid. The other one's going to be assisted by base. Why is this one acid catalyzed? Oh, because sulfuric acid is in the reagent, is one of the reagents. Okay. You had to memorize the mechanism for oxymercuration, demercuration, and we still need to know the same mechanism here. It's called Mercury catalyzed hydrogenation of alkynes. So let's go over the mechanism. And as a review, why don't we review the Mercury reaction of alkynes. So this is review. So you remember I kind of drew out the acetate molecule in the skeletal drawing, and there's two of them, and I joined it by covalent bonds. You might be thinking, wait, I thought it was ionic. Yeah, there's some evidence that suggests there's some covalent bonding, covalent character, if you will. Anyways, pattern is pi bond bonds to the mercury, one of the acetates leaves, and you get the triangle, a three-membered ring. Mercury's going to make 3 bonds, and it's going to keep the acetate group. The mercury is, well, the net charge here is 0. I know it's mercury 2. Acetates are -1s, but right now, if it's a covalent bond, there's no charge. It's now making 3 bonds. It has a formal +1 charge now. And then these carbons, well, one's primary, the other one's secondary. Because the mercury has a positive charge, these bonding electrons are attracted to the mercury. It's as if it's more electronegative. I have to go and look at the electronegativity values. I think mercury's pretty close to carbon, but I'm not sure. But I am sure of this positive charge. So the positive charge is yanking on these bonding electrons away from the carbons, and they're starting to become slightly positive, delta plus. And the secondary one can release the electrons better. It's sort of like a double plus. It's more positive than the primary. So that in the second step, the polar water molecule, or oxygen slightly negative, hydrogen positive slightly, opposites attract. The oxygen's more attracted to that is the secondary carbon and opens up the ring by bonding to this secondary carbon. And this explains Markovnikov addition. The water's oxygen is going to become the alcohol here in the double bond case. When it's a triple bond, oxygen from water will become the ketone oxygen. Okay. Mercury swings over, right? So this bond stays intact, keeping the mercury attached to the end of the chain. Water's going to add here. And then, let me give myself a little more room. Squeeze in acetate, it's still connected to the mercury. Cool. And then the last step that you had to memorize for this reaction from unit 2 is you bring in another solvent molecule, a water molecule, to act as a base, to remove the hydrogen so we can see the alcohol group. And this is as far as you need to go for my exams. In the NABH4 step, hydrogen adds to this carbon and kicks out or displaces the mercury. And then you get the final alcohol product. So that was all review. All right, so now let's try it with the triple bond. Okay, this is not one of my favorite reactions. Because darn it, someone's doing some research and finding out that, hey, here's the mechanism for double bonds. Shouldn't we just add an extra pi bond here and just do exactly the same thing? Makes sense to me. Yeah, but that's not what the experiments are saying. So we're also using mercury sulfate, but it doesn't matter. If you use mercury acetate, mechanism still is not exactly what you would expect. So it doesn't matter which form of mercury. I'm just going to put H plus, sorry, Hg2 plus. And it could be attached to the sulfate, whatever you want to do. But one pi bond connects to the mercury and it doesn't form a triangle. It does not form this. So 1 is a 3 plus. I have to think about that a little bit. Here's the reason why. What's the bond angle in this triangle here? Well, it's an equilateral triangle. It should be 60 degrees approximately. And what's hybridization of this carbon? There's an unwritten hydrogen. There's 4 single bonds. It's sp3. The bond angle should be 109.5. Should be that, but it's actually 60. So there's significant angle strain here. Now this, if this were to form, the bond angle would also be 60. And what is it supposed to be? Well, what's hybridization of these carbons? They're sp2, which means 120. And that's a bigger angle strain. And turns out nature's like, I ain't gonna do it. That's just too much. And that doesn't form a triangle. So what does it do? It acts like hydrogen, and it goes to the end of the chain. Where are my notes? Yeah, it's a plus. You get a carbocation. And now I'm thinking, wait a second, I thought we said the mercury reactions don't create carbocations. Yeah, I know. The evidence, the experimental evidence suggests we are making carbocations. So Cc plus means carbocation, but they don't rearrange. Even if there's a tertiary center next time, they don't rearrange. I don't like this, but that's what we got. Someone needs to study this better. Anyways, this is the mechanism. Why does the hydrogen go over here? It's to create the more stable carbocation. So if the mercury attached to this carbon, put the plus over here, this carbon's primary, whereas this one's secondary. So yeah, I don't like the carbocation, but it does explain my Kavnikov addition, because the water, just like the water up here attacked the delta plus, the water's going to attack the full plus. Okay, and the oxygen uses a lone pair and drags the 2 hydrogens along. And there's an intermediate. It does look very similar up here, so that's nice. What's the next step? Make the alcohol, same way you did before. So add in another water molecule, which acts as a base, and the lone pair goes and grabs an H+. You make an alcohol, and then we feel like, oh, we're all done, aren't we? And the answer is no. For the oxymercuration, demercuration with an alkene, double bond, we didn't have to show this last step because all you did was knock out the mercury and put in an H and you get your alcohol product. But if we were to stop here, knock out the mercury, we get the enol product. That's not the final product. Our final product is a ketone. So now we gotta keep going. Oops, I need to draw something here first. So what we need is the acid. So where's the acid? Remember the reagent was sulfuric acid, water, and mercury sulfate. So your choice, do you want to write H+? Do you want to write H2SO4? Do you want to write hydronium? They're all acids to me. You pick. Well, I got the H+ there. So what happens is that the bond that attaches the mercury will grab an H plus. Okay, so now I need to go to the right. I'm going to go over here instead. So after this bond grabs a hydrogen, well, hydrogen can only make one bond. And so the end of this line must be H, and the mercury has to leave. Good, we don't want the mercury in there anyways. We still have the pi bond, and we have an H. And then we kick out mercury. And now it leaves as H2, it's a catalyst. We started with H2 right here, and we get it back out. That defines a catalyst. Yeah, but we made the enol. And we're supposed to end up with a ketone. We need to do the keto-enol tautomerization. You think I'd mess up the word tautomerization, not the keto. Anyways, we got 2 more steps. It's going to take an acid. And then to help me remember, I'm doing the video. How does this work? Darn it. Remember the product. We got to get the double bond to move. And this carbon at the end needs 3 H's. Right now, there's 1 H here, and there's a second one. There's only 2 H's. So I want this H plus to go here. And that's a little counterintuitive, right? Because if we go back and think about Lewis acids and bases, we usually said the lone pair is a thing that grabs an H plus. So that's a little contradictory. Instead, yeah, I already mentioned this is not one of my favorite mechanisms. All these weird oddities. The lone pair doesn't grab the H plus. The lone pair changes into a new pi bond. This pi bond. So the lone pair, 2 dots become 1 line. And then if you were to draw the double bond now, then that would give this carbon 5 bonds. Ouch. Carbon can't handle 5 bonds. So as the lone pair comes down to create the new double bond, it pushes on this pi bond because it can't stay there. Can't make 5 bonds to that carbon. The pi electrons grab the H plus. So the net change is that, well, you still have the OH group. The lone pair formed a double bond. This pi bond left to connect a hydrogen to the end of the chain. So let's see, if I get it straight, there was already 1 hydrogen written in, so I'll keep it there. And I'll draw the second one. This hydrogen is right here now. If someone else says, well, my hydrogen's up, it doesn't matter. Another hydrogen adds to the end of the chain. Are we done? No. Oxygen's making 3 bonds, so it's formally a +1 cation, and it doesn't look exactly like this one. It's pretty darn close. So now what do we have to do? We have to remove the H and the plus. We have to remove H plus. Didn't we do that before? Yeah, this oxygen's plus. You need to remove an H plus. So bring in a water molecule. Same pattern. Bring in a water molecule to go grab this extra hydrogen. H comes off as H plus. The oxygen's left behind as neutral, and you get a hydronium ion at the end. Whew. That's our longest mechanism yet. Okay, you got it on I was going to say on film. You got it on your computer screen. You can rewind it, slow it down, pause it, take another look at it. Take a break, then come back and look at it. Give yourself some time to kind of absorb this. Whoa, what happened? Did I hit this part of the screen? Oh, I must have went down. Even the computer doesn't want to look at that anymore. Okay, let's just make sure I didn't miss anything. I'm good. Okay. Keto, tautomerization. All right. We're still trying to make connections between alkene chemistry and apply it to alkyne. So we had the Mercury reaction with the double bond that did Markovnikov addition. The hydrogen went to the end of the chain, alcohol in the middle. And then someone says, wait, I want the anti-Markovnikov product. Well, to do that, you do hydroboration oxidation. So as a review, let's put that in here. So if you take a double bond, what are the reagents? BH3, or sometimes it's B2H6, diborane. I like putting in the THF. As I've been looking around the internet and other textbooks, sometimes they leave the THF off. So just be aware if that shows up on the MCAT as just BH3. And then in the second reaction, you add hydrogen peroxide and base. Sometimes it's just written OH minus. And what happens? The rich don't get richer. This is anti-Markovnikov, anti-Markovnikov addition. It's also syn addition. The new alcohol and the new hydrogen add to the same side. Okay, but the pattern is lose the pi bond, add an H and an alcohol, and the rich doesn't get richer. So this carbon has 2 H's, this one has 1. Markovnikov's rule says the hydrogen is supposed to go here. Hydroboration oxidation does the reverse. Puts the hydrogen here and the alcohol here. That was the pattern. Still good to remember that, even though it's back in Unit 2. Let's apply that same reaction, and ooh, yes, the same set of reagents. They work on alkynes. Okay, so the pattern is lose 1 pi bond and add the alcohol in an anti-Markovnikov fashion. So remove 1 pi bond, and I'm going to keep 1, and put the alcohol in an anti-Markovnikov fashion. And the hydrogen goes on, and it's still syn addition. Yay, are we done? Now you get used to my sarcasm here. No, because this is another darn enol. We got an alkene attached to an alcohol again. Nature poo-poos this. I don't like that. So put this in parentheses. It is an intermediate. It's not the final product. You do the rearrangement, which you know is named the Keto Enol Tautomerization. And the pi bond goes to the oxygen. And the other hydrogen goes to this carbon. So right now, this carbon only has 1 H. Now it has 2. What's the name of this functional group? It's an aldehyde. Yeah. Okay, so chemists kind of get excited about this. If you have a triple bond at the end of a chain, by choice of reagents, you can either make a ketone or you can make an aldehyde from the same starting material, this molecule with the triple bond. That's powerful. You get choices. You can decide, do I want a ketone or an aldehyde? Very cool. Okay, key points. I think I hit most of these. It's anti-Markovnikov. No carbocations, no rearrangements. Yay on that. Last 2 steps, keto tautomerization, but now it's base catalyzed. Wait, why is it base catalyzed? Oh, because you're using a base. Okay, but, that's information we'll use next semester. I'm hoping you hang on to these key concepts. You'll review them when we see, new stuff next semester. Memorize the mechanism. What was the mechanism, man? Well, you only have to remember the first part of hydroboration. So let's go up and review it for the ketone, for the alkene. Yep, the alkene. This is one of my favorite mechanisms because it's just one step and it's done. Well, it's not really done. It's all we have to have memorized. So take an alkene and then that's a W with BH3, but rewrite the BH3 as BH2 and highlight one of the bonds to the hydrogen. So this molecule is BH3. And now the mechanism says that the bigger 3-atom group, it's bigger than this 1-atom group. The bigger group will be away from the bulkier part of the alkene. So the primary carbon is smaller, less bulky. Secondary has more stuff hanging off of it, another carbon that's bigger. So this is kind of big. And the BH3 molecule aligns itself so that the biggest pieces are farther apart. That explains anti-Markovnikov addition. The pi bond attaches the hydrogen, attaches this H between these two atoms, carbon and H. And this bond breaks and connects the boron to this carbon. And then there's more steps that are not required for the mechanism or for your exams. There are more steps in the mechanism, but you don't have to write them out. That's all you have to do. So what happens is that this boron has 2 more H's. It can react with 2 more alkenes, still adding Markovnikov, anti-Markovnikov, and then hydrogen peroxide and base will change the boron carbon bonds into alcohols. That portion's not on the exam. Okay, just repeat this with an alkyne, and yay, it's exactly the same. The only difference is you don't have 1 pi bond, you got 2. So maybe I'll use this pi bond to connect the carbon to the hydrogen. This bond connects over here. This pi bond didn't move, it's still there. And now you put the H in place, you have the BH2, and this is simply an alkene with a boron on it. Nature says, yeah, I'm good. And so this is fine. Later on, the boron gets changed to alcohol, and then nature says, whoa, you made an enol again. So at some point later, you get the enol, which tautomerizes to make the aldehyde. And I put in parentheses because that portion's not part of the mechanism that you have to put on your exams. In other words, I only require this step to explain the anti-Markovnikov behavior. Phew, nice shorter mechanism. Okay, what else we got? Oh, we're just gonna highlight this again. That's a good idea. So let's define what a terminal alkyne is. Remember like airplane terminal? That's where the airplane lands, its final stop. You're at the end of your route. Well, an alkyne's at the end of the chain. So that's where the terminal part comes from. So examples of terminal alkynes, here's one. Here's another one. I almost put the triple bond there. Big mistake. That would give this carbon 5 bonds. So I'll put it here. Okay, those are terminal alkynes. Internal ones are where, well, as you would guess, the triple bond's inside the chain. So put the triple bond here. Can't put the, if the ring was bigger, maybe I could squeeze a triple bond in there. Remember SP hybridization, 180 bond angles. How you can get a 180 bond angle here and still close up the ring? You need a large ring. 7, probably 8 carbons or more. Let's see, where were we going with this? The more interesting triple bonds are the ones that are end of chains, because here is where you get different numbers of hydrogen. This alkene hydrogen has no H's. This one has 1. So if you do the Mercury reaction, that's M, I want H. The Mercury reaction, again, change of reagents. Mercury sulfate, sulfuric acid, and water. Then you get the Markovnikov product. This carbon had 1 H, and now it has 3. Rich gets richer. And you make a ketone. But if you use anti-Markovnikov chemistry, which means add your borane and your THF in the first step, and later add hydrogen peroxide and base, then the rich doesn't get richer. This carbon had 1 H, this one had none, and now it turned into an R. R stands for the rest of the molecule. It's a nice shortcut that chemists use. R is not on the periodic table. It's the remainder of the molecule. So what's happening here? Let's say maybe that's a methyl group. So you start with this, and then your molecule, this carbon, is going to get the H's, 3 parts, sorry. Methyl, methyl. Next carbon, CH2. Last carbon is going to get the oxygen that's double bonded as an aldehyde. So starting again, looking at this triple bond at the end of a chain. This carbon has no H's, this one has 1. The one that had none actually got more hydrogens. It has 2 H's. This one still retains a hydrogen ahead. More importantly, you get an aldehyde. Okay, it's not on the test, but hey, chemistry majors, there's a term you'll see later in your chemistry careers, regiochemistry. I may have referred that, mentioned this before. Regio sounds like region, different region of the country, different location. So regiochemistry is concerned about locating functional groups. In this case, the C-double bond O group. Mercury will put the C-double bond O at this location. Borane will put it at this location. And it's a big difference. If the double bond O goes on the first carbon, it's a ketone. If the double bond O goes on the second one, it's an aldehyde. Regiochemistry, yay. Okay. Ooh, we got 2 more reactions left. If you ask me, out of all the reactions we've discussed or will discuss in the first half of Unit 3, if you ask me, which one's the most important one? Oh, I wouldn't hesitate. I would say it's this one. Okay, so maybe that got your attention. This is the alkylation of terminal alkyne reaction. It's also known as extension of terminal alkynes. Okay, so what happens here is that you just make the molecule bigger. Ooh, and if you're in the habit of trying to make big molecules, this is a great reaction. Okay, so what do you have to do? You have to alkylate or add alkyl groups, add carbon to the ends of your triple bonds, the triple bonds that are already at the end of a chain. So if we have a triple bond at the end of how many carbons? 1, 2, 3, 4, 5. Okay, we got 5 carbons there, the end of the triple bond. You kind of have to get this ready to accept more you have to get it ready to accept more carbon because we want to alkylate it, add more carbons to it. Carbon can only bond 4 times. To make room for more carbons, you have to detach this hydrogen here. And we're going to do it with a very powerful base. Okay, that's a little unusual. CH bonds are usually not acidic, right? Alkanes are not acids. The C's with H's don't fall off. The C's don't donate H+, they're not acids. But something is weird about that triple bond, that sp hybridized carbon is weakly, very, very weakly acidic. It's so acidic that sodium hydroxide at room temperature, even though sodium hydroxide is considered to be a strong base, it's not strong enough. We have to amp up our base. So I'm just going to take a little detour, go back to the periodic table, and remember that on the right-hand side is carbon, then nitrogen, then oxygen, then fluorine, then neon. Okay, if you give fluorine an extra electron, fluoride ion is a weak base. If you give oxygen electron, like in hydroxide, hydroxide is a strong base. Seeing a pattern yet? The very electronegative atom likes being negative. This one's less electronegative. It's having trouble being negative. It's a strong reactive base. What if we put a negative charge on the nitrogen? Ouch! Very unstable, very reactive. You can create it, but it's going to be a very, very powerful base. So if you start with ammonia, NH3, take away an H, you get NH2, which is an anion. So pair it up with sodium as a cation, at least make a neutral salt. something you can add to your alkyne, and now you have a very powerful base. And it'll remove this hydrogen. So I'm going to show the mechanism because it's nice and short. Yay, short mechanism. Nitrogen, when it's negatively charged, sodium is positive, nitrogen has 2 lone pairs, right? Ammonia, NH3 has 1 lone pair. You steal an H, that line becomes 2 dots, a second lone pair. Okay, ammonia, that's ammonia. This is called sodium amide when it's as a base. The lone pair will grab this H. These bonding electrons make a U-turn and become an anion, a carbanion. And if you thought nitrogen had trouble with that negative charge, carbon's going to have even a much harder time with it. It's even less electronegative, less willing to become negative. It's just something weird. Nature, she makes the rules, and I haven't quite figured out why, but this carbon with the negative charge is actually a little more stable than nitrogen with the negative charge. I don't understand that so much. But I know it's true because water runs downhill. It tries to make things more stable, kind of find the lowest point, lowest energy point. Somehow nitrogen with negative charge is strong enough to rip away this hydrogen. And if I'm showing the mechanism, then when NH2 grabs the H, it becomes ammonia. Is the sodium still stuck here? No, ammonia is neutral. Sodium is positive. The sodium is now going to stick to the carbon as an ionic bond. Opposites attract. And it turns out this carbon is not strong enough to remove that H. I guess technically it's an equilibrium, but the equilibrium lies with carbon with the negative charge. It's more stable than nitrogen with negative charge. Go figure. We're not done yet. We're trying to make this a bigger molecule. Well, here's what you do. You can add in a carbon attached to a halide, except fluorine. So maybe I'll add bromine. And in the mechanism, bromine is more electronegative than the carbon, right? Bromine's closer to fluorine, the bully of the periodic table. Farther away, bromine is closer to fluorine. Carbon's farther away from fluorine. So that's the trend of electronegativity. The closer you are to fluorine, the more electronegative you are. So bromine's more electronegative than carbon. So there's a slight positive charge on this carbon. And we already said carbon does not like being negative. So this negative charge is very attractive to this slightly positive carbon. This lone pair will actually bond to this carbon. And the bromine that's been yanking through its electronegativity, yanking all these electrons, will actually break away as bromide ion. And then these 5 carbons, we start with 5, will then attach the methyl group to the end of the chain. And now it's a chain of 6. And in the mechanism, you get Br minus. And hey, sodium's just a spectator ion. Sodium's not going to hang around here. Everybody's neutral. Sodium's going to be over here with the bromine. You get sodium bromide as a byproduct. That is cool. Turns out you don't have to only use methyl bromide. So if you create that anion, and if you don't want to put the sodium in there, I won't dock you points. It's just a spectator ion anyways. So you could say, hey, my carbanion is going to react with a different molecule. Maybe I have a ring here, and at the end of this chain is a chlorine. Okay, so where's the slightly positive carbon? Over here, closer to the negative charge? No, sorry, that sounded mean. Chlorine is slightly negative, so this carbon is slightly positive. So the lone pair is going to attach to that carbon and kick out the chlorine. So just copy your starting material, 5 carbons, and the attachment is to this carbon. So the attachment is to this carbon, right? So you already have a carbon there, so don't, yeah. Gotta be careful when you draw the product. This carbon and this carbon are the same, and then there's another carbon, then the ring. Another carbon, then the ring. A nice check is, if you were to name this, we'll learn that in another video. You know, start numbering out the triple bond. This is 1, 2, 3, 4, 5. If you had to name this is 1, I don't know, clockwise, counterclockwise, whatever. 3, 4, 5, 6. And there's a 7th one here. You don't number it that way, but if you're counting them, you do. Sorry. So I got 5 carbons in this molecule. I have 8 in this other one. 5 plus 8 equals 13. I better have 13 carbons down here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13. Good. So you should check that, because I take off a half point if you add an extra carbon or you accidentally lose a carbon. Got to predict the products correctly. Okay. All these details. There's a few more details here. We're not going to go over the mechanism today. Nope, I lied. We already went over the mechanism. I'm thinking about the next reaction. This mechanism is very common. This part right here, we have a lone pair bump out a halide. We'll learn that later in this unit. The name of this type of mechanism is called SN2. It stands for substitution by a nucleophile. That's bimolecular. Yeah, we'll explain all that later. Anyways, as you're reviewing your key concepts later, SN2 will make more sense. Right now, you got the base, removing the H, makes a carbanion, and then in a single step, lone pair hits the carbon, kicks out the halide, 2 curved arrows, and product. What kind of molecule can you put over the arrow? What kind of halide? They have to be the methyl halide or a primary halide. If you use a secondary one, so here's a secondary one. Remember how you classify the halides? You try to talk the halide, hey bromine, what degree are you? Primary, secondary, tertiary, or quaternary? Guy says, I'm shy. The carbon that's attached to it says, yeah, he's kind of shy. Here, let me answer. Let me check myself first. What am I? What degree am I? Oh, I got a carbon on my left, carbon on my right. 2 carbons, I'm secondary. Bromine carries the same label. This is a secondary carbon, secondary halide. Well, it turns out that this carbanion is kind of big and kind of bulky. It's got 5 carbons there and all the attached hydrogens. And that carbon, that carbanion, is really unstable. And so what happens is if you have a secondary or if you have a tertiary halide, this is even bulkier, you get side reactions. This carbon has a tough time sneaking past all these hydrogens. There's a methyl group on each part. And it gets desperate and actually will steal a hydrogen instead of attaching to that carbon. We'll see that later. We actually have a name for that type of reaction. It's called an E2 reaction later this unit. What you need to know now is if you try to use this halide or this one in the above reaction, it fails. Don't fail on the exam by using these. Yeah, don't use a secondary, tertiary halide because it doesn't work. So that's why you lose points, because it's an inaccurate prediction. It doesn't work. For right now, this semester, I'll be sticking to NaNH2 sodium iodide. That'll be my choice base this semester. Next semester, though, we'll see that other bases can be used. And there's other molecules we're going to create that actually will become bases strong as or stronger than sodium amide. So we'll have to be aware of that. Right now, though, I just want to introduce that. I just want to plant a seed. NaNH2 is not the key here to make this work. So a lot of students get fixated, and I think it's a good idea. They say, ooh, NH2, NaNH2, this is alkylation. And that's not always true. You can have a different base here, and it could still be alkylation, but we won't see that until next semester. And I just lied again. Maybe in the homework, I won't put it on my exams, There are some cases where you can get sodium hydroxide to work as a substitute for sodium iodide, but you have to heat it up to make it more reactive. The danger there is that if you add heat, you might burn your organic molecule. So it's not a good idea. It doesn't always work. But I think there's a homework problem or two that does that. So I just want to alert you to that. If you see sodium hydroxide over the arrow here, followed by a methyl halide or a primary halide, the homework problem is trying to do this alkylation reaction. And it will work in the lab under certain circumstances. Cool. And the last, most important thing is count your carbons. Make sure that the number of pieces you're joining together have the same number of carbons before and after. Phew, thanks for hanging in there as long as you have. One last reaction. We talked about how to take the triple bond and turn it into other functional groups. Well, let's talk about how to make a triple bond. So how do you synthesize them or make them? Well, one way of doing it is through a dehydrohalogenation reaction. And there's the breakdown. What you want to do is detach both a hydrogen and an adjacent halogen to make room for the triple bond. So let's start with a pair of halides. And we'll use the base again, sodium amide. And if you want, you can add one equivalent. See how things kind of go full circle? We used 1 at the beginning of this video, and here it is at the end. Okay, if you use one equivalent, then this acts one time. This is a base. Bases accept H+. So there's a hydrogen here and another one here. I don't know, maybe I'll pick the first one. The lone pair, if you were to show a mechanism, is going to grab this hydrogen. And I probably shouldn't be doing it. Yeah, it says the mechanism will be shown later, but I'm going to preview it. So the mechanism portion is not on. Well, yeah, it will be. By the time we get the exam, we'll see you too. Sorry. Here's the mechanism. Lone pair on the nitrogen grabs H+. These electrons become a new pi bond, and this carbon's already got 4 bonds. So how's it going to make a pi bond? Another bond? Well, the electronegative bromine's yanking on these electrons and actually yanks them completely off and takes off as Br-. And your byproducts are, well, NH2 grabbed an H, so you have ammonia. NH3. This bromine left is Br-. Where's the sodium? Spectator ions, just following the charge. There we go. Ammonia and sodium bromide are the waste products. You get an alkene if you use one equivalent. You still have a hydrogen here though, so you can treat it one more time. And I won't show the mechanism, but the nitrogen is going to remove this hydrogen. This pair of electrons will become the triple bond. Bromine will leave again, and you get the triple bond. And you make an alkyne, yay! And of course, you can do the whole thing in one step. You don't have to make the double bond first and then the triple bond later. You can just say, hey, add a bunch of base. Use an excess, right? If you don't use 1EQ, and you just leave it as a chemical formula, what you're saying is I'm using an excess, as much as needed to get everything to react if they're going to react. Okay, so there's 2 bromines, there's 2 halides, so you immediately get, I don't know, immediately, but the final product is a triple bond. Cool. Any last notes here? It's an E2 mechanism. We'll see that later. One equivalent base makes alkenes. Okay, so if you need an alkene, you can take an alkane with a pair of halides and actually add one equivalent and stop at the alkene. Maybe that's what you want. Oh, some students, I don't know why, can't remember the case, but they say, well, there's a hydrogen over here as well as here, so can't I make this? And that's an allene. where one carbon's making a pair of double bonds. And nature, she makes the rules, and the answer is no. Alkenes are just not that stable. The triple bonds are more stable. So if given the choice, and nature gets to make the decisions, instead of pulling off this hydrogen, she's going to pull off this one instead and make 2 pi bonds here. Yeah, make the alkyne instead. And then we already mentioned in the previous reaction, NaNH2 is not special. It's a good base, but there are other bases, some exotic bases. We'll see that next semester. Planting a little seed, just to let you know that there are other bases that can do the can make triple bonds. Okay, I think that's it in terms of new reactions. I got a last couple of points here in my notes. I want to just point something out. What was it? Oh yeah. Here, just take a note of this. We use the same reagent to do 2 different things. Right, so this new reagent, sodium amide, can make triple bonds, but can also extend a terminal alkyne. So you can get clever and use them both in the same reaction. Nothing special about bromine. You can have chlorine there. So what happens if I use NaNH2 and I don't write 1, 2, or 3 equivalents? It means I have an excess. I use as much as needed to get all the reactions to happen. So what happens? Well, the first equivalent is going to remove, so one unit of base will remove 1 H and 1 Cl. So I don't know which one. I should think about it. It's probably this hydrogen that removes first. And then this one, sorry. This will be, let's undo that. It's probably going to be this. We'll talk about that later. But anyways, one equivalent probably removes the primary hydrogen, not the secondary one, because it's less crowded. So the first equivalent of sodium amide will make this, but we're saying we're using an excess. We're not done here. So add a second equivalent of NaNH2. So you added a big mixture, big amount of this. First one attacked it, made this. More of this attacked this product to remove the other H and the Cl to give you the triple bond. But there's a hydrogen at the end of the triple bond. So now your third equivalent of NaNH2 can react with this hydrogen and make the carbanion as your final product. That's not your final product because that's very reactive. You have 2 choices. You can alkylate it, which is probably what you're intending to do anyways. Let's think of something else. I need a primary halide. So when I put iodide on a carbon, that's primary. And then, I don't know, how about we have an H and a methyl here and another methyl there. And then this carbon is going to connect to these carbons. Did I lose any carbons? Start with 5 here, 5 there. I got 5 here also. And then this carbon connects to the carbon that used to be attached to the halide. There's your product. If, however, you said, I really just want the triple bond, well, this is a strong base. It wants an H, so give it a base. It wants an H. Give it an H plus. So you can add hydronium ions, or you can add water. Water's a weak acid, and that will allow you to just get the triple bond. Okay. Someone might be asking, wait, do I have to memorize add water here And the answer is no. If your goal was to make the triple bond from this molecule, you might want to put in 2EQ so I know that you just want to remove 2 chlorines, 2 hydrogens, and stop at the triple bond. There you go. That'd be good enough for me. Okay, that's plenty for now. Thanks for watching.